In this video, we're going to be looking at question 4 of the Unit 3 sample paper for the IAS Chemistry course from Edexcel. This question is the last question in this paper, and it is focusing on the water of crystallisation calculation in sodium carbonate. So the students were given hydrated sodium carbonate and asked to heat it until no more of water of crystallisation remained, and we had the anhydrous sodium carbonate, and you can see that in this equation here. The instructions that they were given was to weigh the sample of the hydrated sodium carbonate in a pre-weighed crucible. We're going to then heat the crucible containing the sample to remove all of the water of crystallisation, allow it to cool, and then re-weigh the crucible. And the table shows all of the results for this student. And for part A, for 2 marks, we want to complete the table. So we've got the empty mass of the crucible, which I'm going to label as number 1. We've got the mass of the crucible and the hydrated sodium carbonate, which I'm going to label as 2. And then the mass of the crucible plus the anhydrous sodium carbonate as number 3. If we want to work out the mass of the hydrated sodium carbonate, we are going to take number 2 and we are going to subtract number 1, because that is the crucible plus the hydrated minus the crucible. And that will give us an answer of 6.70. And it's very important that you put the 0. If you write 6.7, you will not get the mark. Everything else in this table is to 2 decimal places, so your answer must also be to 2 decimal places. To calculate the mass of the anhydrous, we're going to take number 3 and subtract number 1, because again, that's the crucible and the anhydrous minus the crucible, and that gives me a value of 2.62. And now the difference between these two numbers, or the difference between 3 and 2, is going to give me the mass of the water, which is 4.08. If you get 1 or 2 of them correct, you will get 1 mark. To get all 3 numbers, then you get 2 marks. For part B, we want to calculate the number of moles of water that has been removed on heating the hydrated sodium carbonate. So if we're calculating a number of moles and we have a mass, we are going to need an MR. So the MR of water is going to be 18. So to calculate the number of moles, that is mass over the MR, and the mass we just said is 4.08, and we're going to divide that by the MR of 18, giving me a total of 0.227 moles. A nice easy mole calculation for 1 mark. If you are unlucky enough to get the first part wrong and you mess up and you get the wrong mass of water, you will get a transferred error here. So you will lose the mark in part A, but not in part B, as long as you use the number correctly. For part 2, we want to calculate again the number of moles, this time of the anhydrous sodium carbonate formed after the heating. So we're going to again get our MR of Na2CO3, and you of course have a data book, you have a periodic table, and you're just going to look up the different atomic masses and do the multiplication, and you will get a mass of 106 grams per mole. And once again, number of moles is M over MR. We're going to take the mass of the anhydrous sodium carbonate from the table as 2.62 over the 106, giving me a number of moles of 0.0247. 1 mark for the MR, 1 mark for the number of moles. Now we want to use those answers to calculate the value of X. So just as a reminder, our water had the number of moles of 0.227, and our carbonate had 0.0247. We want to calculate the value of X and give our answer to 3 significant figures. You will get a mark for getting it with the correct number of significant figures, so please make sure that you do pay very close attention to that. And in order to work out X, for a water of crystallisation question, it is always the same. Your X is going to be the moles of the water divided by the moles of the anhydrous substance, in this case, the sodium carbonate. So our moles is 0.227 divided by 0.0247, and that is going to give me an answer of 9.19. Now, you may get a slightly different answer just depending on your rounding. In the mark scheme, they say 9.17, but you will be able to get a bit of a range depending on what values you use. The mark scheme does say the answer to part 1 and part 2. So don't worry too much if your answer doesn't match exactly what's in the mark scheme, as long as you're using your numbers correctly. In the mark scheme, they've used about 8 decimal places, whereas in the exam, you're more likely to use 3, maybe 4 at maximum. So we want to make sure we give it to 3 significant figures. Therefore, our answer is 9.19. Now, of course, when it comes to what X actually is, we would class that as 9 moles of water. So in reality, we would have Na2CO3.9H2O. But this question specifically asked for 3 significant figures, so please make sure that you do use that. Part C is a nice percentage uncertainty question. So each use, and each is in bold for a reason, it's there to remind you of something. Each use of the balance to find the mass reading in the table has a maximum uncertainty of plus or minus 0.005. Calculate the percentage error in the measurement of the mass of the crucible and the hydrated sodium carbonate, and they're reminding you that that was 26.06. Now, when it comes to using a balance, because we have to have a 0 at the start and we zero the balance, then we get the balance reading at the end once we put the crucible on it, we always have to multiply by 2, because the 0 at the start has an uncertainty of plus or minus 0.005, but so does the 26.06. So to work out our percentage uncertainty, we are going to do 2 times the value of uncertainty over the actual value that we used times 100, and that is going to give me plus or minus 0.0384%. So actually quite a small percentage uncertainty here. Moving on to part D, the data book value for X is actually 10. So we have calculated X to be 9.19, but the data book says it's 10. One student obtained a value of 8.63 and another student obtained a value of 10.79. So you can see both of them are slightly wrong. But that can be expected with experiments like this. As long as you can explain why it is wrong, then you might do the reaction again to see if you get the correct answer. You would never do a practical like this just once. So we want to be able to explain the practical errors. So what were the issues that were done in the actual procedure that could have led to each of these values? So we have to look at both of them. If we start with student number 1, who got the 8.63. 8.63 is obviously too low. And the reason that it is too low is because not all the water of crystallization has been removed. So we clearly have some water being left over. That's our first mark for saying why that 8.60 is possible, and the practical error is because remember we're using the word explain, so we must be saying because it has not been heated, either been heated for long enough or strongly enough. So we're getting a lower value than expected because we still have some water left over because we have not heated it strong enough. For the second student, they've got a value of 10.79, and we know that that is too high. So we have went over. And what this looks like is we have apparently too much water has been removed. Now, that's just looking at the number, or potentially some extra material has been lost. Two possible ways of looking at it. And then the reason why is because we must have, it looks like we've either lost too much water or we've lost some extra material because some solid has been lost from the crucible. What we might have found here is that there potentially wasn't a lid on top of the crucible, and some of our solid, as we're heating it, has jumped out of the crucible, giving you a mass that should be lower than it is expected. So it's looking like we've removed too much water or we've lost some of our solid. And then the last question is looking at an experiment involving a titration that could be used to determine the value of X, and we want to list the essential steps in the practical procedure. We don't have to talk about how the data is actually used to calculate X. So in reality, this is another way of saying how to do a titration. And how do we do a titration of sodium carbonate, something that is a base? So whilst this looks a little bit scary at first, it's actually much easier than you think. 4 marks, how do we do a titration? Well, for any titration, first of all, we must always have a standard solution. So we want to dissolve a known mass of the sodium carbonate, and that's of course our solid, and we're going to dissolve it in water to make a standard solution. So we need to know what concentration that is, and then we'll be able to see how much is then going to react with our substance in the burette. So we then have to titrate this with a known concentration of HCl. Now we could use sulfuric acid or nitric acid, but we tend to use hydrochloric acid in titrations. That usually is the sort of best acid for titrations. We need to, obviously for any titration, always use an indicator. So we are going to use methyl orange, or you could potentially use phenolphthalein. Either of them would be acceptable. Don't say litmus paper or litmus or universal indicator. Those should never be used in titrations. It's always only methyl orange or phenolphthalein. And then, like every single titration, we are going to repeat to obtain that amazing concordant values. Every single time we must get concordant values, and that means that they are within 0.2 centimeters cubed of each other. So we have our standard solution of our sodium carbonate. We're going to titrate it with the HCl using a methyl orange indicator, and we're going to repeat to get our concordant titer values. Once we then have those values, we would then analyse the data and do calculations. But as we said at the start, the question does not ask us how to do that. It is purely how do you do the titration. So that's a 16-mark question, all to do with water of crystallisation. The part at the beginning about the calculation and the heating to constant mass and being able to work out X, that's a very, very common exam question. So I would make sure that you do practice that and you remember that it's always the mass of water, the moles of water divided by the moles of the anhydrous substance to work out X. If you have any questions on anything that we have done in this question 4, please feel free to leave a comment below and make sure you check out the rest of the playlist to see how we answered questions 1, 2 and 3.